Okay, so the recording is starting now. Okay, so today we will kind of do the last bit of the transforms, the Laplace transform, and then move on to the section on control theory, just the first bit there on describing a system. So I'm going to start with exercise 16, which is to compute the Laplace transform of the sinusoid ut sine omega naught t. And you want to locate the poles and zeros. So, with the Laplace transform, we almost always see this ut over here, mainly because when you're multiplying with e to the minus sigma t, which is what you're doing to sort of reduce the value of the function. So, just as a brief reminder, when you have a function which is even like a unit function like this, or an increasing function like that, what we're doing in the Laplace transform is to multiply it with e to the minus sigma t, and that is going to take the product and make it a reducing function rather than keeping it increasing. So then the integral is going to evaluate properly. And so for that, we want basically we need to have something that is multiplied by e to the sigma. You want t to be positive and sigma to be positive as well, but you certainly want t to be positive. So we almost always see the ut multiplying the functions for which we want to find a Laplace transform. Otherwise, we get into trouble. Ut meaning the unit function, which is this function over here. This is ut over here. So it's the integral of the delta function. Okay, so to go to this, we basically use the Euler formula to write sine omega naught t as as ut. So this is going to be ut, and then the inside part is 1 over 2j, and then e to the minus j omega naught t. Okay, we'll just do it that way. Minus e to the minus j omega naught t. Oops. So that's just rewriting sine t in this way. And then what we can do is we can take the Laplace transform for this. So x of s, if this is x of t, then capital X of s is given by this integral over here, integral minus infinity to infinity, ut, and then just exactly what we had over here, which is over 2j e to the j omega naught t minus e to the minus j omega naught t e to the minus st dt. That is basically by definition. And now what we do is that we essentially use this ut to make this going to be 0 in the integral. So if you do that, then that becomes 1 over 2j integral 0 to infinity e to the j omega naught t, and then we bring the e to the minus st into it, minus e to the minus st dt, minus integral 0 to infinity e to the minus j omega naught t, again the same, minus e to the minus st dt, e to the minus st dt. And these are exponential, so the evaluation is really straightforward. And basically, when you set e to the j omega naught t, we set okay, let me just do it properly. So e to 1 over 2j. So this integral is going to be integral 0 to infinity e to the j omega naught minus s t dt minus integral 0 to infinity e to the minus j omega naught plus s t dt. And so this is of the form essentially e to the x dx. That's what you see over here. And so when you have a function of that form, the integral is going to be given by just the, you just take the limits for 0 and infinity, 1 over 2j, 1 minus s minus j omega naught minus 1 over s plus j omega naught which becomes, if you simplify that, omega naught over s square plus omega naught square. And so that's the, and the region of convergence is real of s is greater than 0. So you have, that's the region of convergence over here. I don't think that's very easy to read and read. The real value of s is greater than 0. Real value of s meaning sigma. Okay, any questions about this? Okay, and so we need to know where the poles are and where the zeros are. So the poles are where these values go to 0. So the poles are at s equals plus minus j omega naught. That's where the poles are. And then the 0, the transform is, if omega naught is 0, then the transform is 0. Then then basically we get the x of s equals 0, because you have this form over here, this one over here. And if it's not 0, then it's never 0, because we're never going to get a value of 0, or we're never going to get a value of omega naught. So if omega naught is non-zero, then it doesn't matter what s is, it's going to be non-zero. So we don't get a 0. Okay, any questions about that?
Quick question about this, about the 0. So we'll say that this does not have any 0, right?
Unless omega naught is 0.
Is that called a 0 then of the Laplace transform?
Well,
the entire thing is 0.
Yeah, you're right. So it's not a 0 of the Laplace transform. That's right. So let me see. So let me be precise here. So the Laplace transform, the 0 of a Laplace transform is the values of s for which the transform is 0. And so there is no value of s for which the transform is 0. But there is a value of omega naught for which the transform is 0. So that's when omega naught is 0. So it's yeah. Does that clarify things, or is it making?
So there is no 0 then, right? Because 0 is only a value of s for.
That's right. Yeah. So there is no value of s for which the transform is 0. That's right.
Can we say that when there are infinite zeros when omega naught is 0?
Yeah, you can say that. I mean, the thing is, we are interested from the perspective of the system to understand when is the transform 0. And the zeros of the transform are where it is, where the values of s which is 0, but you can have an external parameter like omega naught, which also makes it 0. And so if you just want to be careful, you can say, yeah, the transform will be 0 if it's going to be, if omega naught equals 0.
Right. Thank you.
Yeah. Okay. Any other questions? Okay, so let's go to the 17 then. So 17 is basically saying let's compute the Laplace transform of the signal ut. Again, we see that same ut sine omega naught t minus t naught. And so what you see over here is that this is basically a time shifted sine. It's a time shifted sine where we're shifting sort of the sine wave to the right by value t naught. And we know that multiplying, so we know the time shifting rule says that if you time shift by t naught, this is the same as multiplying by e to the st naught. Is equivalent to e to the st naught. And so we know that that this is the value over here. So the Laplace transform, so we can say something like this, ut of sine omega naught t has the Laplace transform of omega naught over s square plus omega square, omega naught square, which implies that u of t sine omega naught t minus t naught has the Laplace transform of e to the s t naught, omega naught over s square plus omega naught square. So it's just basically it's a trivial application of the time shifting rule.
Yeah. Should it be a negative exponential?
Oh gosh. Should it be a good explanation? I'm sorry, did I read the rule incorrectly? Just a minute. I think you're right, but I just want to confirm that. I'm just looking at the table. I think the time
Page
shift rule.
213, fourth one.
The fourth one. I'm sorry, 213, the fourth one. Yeah, I think time shifting. Yeah, we're right. E to the minus st naught. You're right. Thank you. Sorry. Yeah. So that's a typo in my notes as well, which I will fix. Okay, give me 1 sec. I'm going to note that down on my notes so that I don't miss that. Problem with writing a book is that there are infinite opportunities for making a mistake. Okay. All right. Okay, let's go on to the next one, using the Laplace transform to solve the system.
I had a question about this one.
Yeah.
We time shifted the sign, but we didn't time shift u there. So is it the transform of u t minus t naught sine omega naught t minus t naught equal to that?
Yeah, so you're right. So I should be careful here. So let's see, we're time shifting to the right by t minus t naught, right, of the sine function, right? And
yes.
so if you think about it like this, I have the sine function over here. Sorry, it goes the other way around. That's the cosine function. If the sine functions, it goes like this basically. And what I'm doing is I'm shifting it. So let's see. So what I'm doing is I'm shifting it to the right by t minus t naught. And we do, what about you now? Let me see. We can view this over here as the time shifted value, and then the ut is, should we say ut minus t naught? Let's see. Yeah, so if let's say t naught is positive, if t naught is negative, then you're going to get into trouble, maybe get into trouble. Let's see. So
you think my approach of this question is that you expand the sign, the sign part with the formula sine a minus b.
Right. Okay.
Yeah.
And then okay.
And then everything are just fine. Yeah.
I see. So let's see. So remind me. So sine of a minus b. What is that going to be? It's going to be.
I think that equals to sine of a cosine of b minus cosine of a sine of b.
Okay. And so in our case, this is going to be, I don't remember, this is, I literally studied this decades ago, so I don't remember the sine formula. I see, so if you expand it this way, so then you're going to say it's sine of t cosine of t naught minus cosine of t sine of t naught, and then you're going to expand this out.
And then you just do the transform for this. Yeah, because cosine of t naught and sine of t naught are constants.
These are constants, so, that's true. Yeah. So this is going to be cos t naught. And then we have the transform of sine t naught. So we got to put ut for both of them. So we're going to just say, yeah, yes. So that allows us to put u of t here, u of t, and then, oops, oh, that's interesting. Okay. So that becomes u, so we say u of t cos t naught. And then so we get sine t, you're right. And then minus sine t naught, that's just a constant, cos of t. And then we can take that, the transform of this, the transform of this is going to be cos t naught. And then for sine of t, we get omega naught square over, let me remember that, omega naught square, omega naught over s squared plus omega naught square. So omega naught over s squared plus omega naught square minus sine t naught s square over square plus omega naught square, if I remember correctly, or is it just a second? What's the transform of a sine cosine? S by S, not S squared, it's S. Sorry. Okay, this doesn't look the same to me as what I had over here. E to the ST not omega. This one over here looks different. So I mean, this is certainly correct. What you're suggesting is absolutely correct. And to be honest, what Vasundhara asked was a very good question about what about U of t, and so let me think about it, and I will get back to you on this. I'll just send email on Moodle what to do about U of t, because I need to think some more about this. To be honest, I had not thought about this, but the answer over here certainly is correct. I mean, then there is no issues here. This is definitely the right thing. It might reduce to that. I have to think about that too. But I'll get back to you on that. Do we need to do a time shifting of U of t or not? I hesitate to do things in real time. But yeah, any other questions?
I had a question about one of the properties mentioned in the notes.
Okay.
That frequency shifting.
Right.
The region of convergence.
Okay.
In that, by multiplying by e to the AT, our result is now x of s minus a.
Right. So that's on page 213. That's yeah. Okay.
Yeah.
So you're saying okay. So we're saying that if you multiply by e to the AT. Right. Okay.
But then it looks like the region of convergence should be alpha is less than real of s minus a is less than beta.
Minus real. Okay. So let me double check. So I got this table from a standard table, or actually, if I remember correctly, I referred to Wikipedia for this, if I remember correctly. So let me go back to my Wikipedia and see what it says, because this is just a standard table. I have really nothing to add here, but let me see if I can get to Wikipedia even. I have a fairly complicated setup right now in my, let's see. There's a very nice table of transforms in Wikipedia. There is a nice source for this, but I hope I didn't make a different mistake. Okay, let's see. Table of selected Laplace transforms, and where did I put it? Time shifting. Right. Okay, I think I'm not going to do this in real time either. So let me get back to you there. If there is an error in there, I'll have to look up frequency and time shifter. So this is you're saying this frequency shifting may have an error, so I'll look into that. And again, I'll get back to you guys on that. So that's frequency shifting. Okay. Are there any other questions? All right, so let me move on then to the solving the system part. And here the basic idea is to essentially compute the product of the transfer function and the input, and then you take the inverse transform. So right, so we have in this case, let me just get to the right place over here. So okay, so we're given that the input is the impulse response h of t is given by cos omega naught t, and then the input is given by e to the minus t ut. So we can then use this to say, okay, the Laplace transform of this is h of s and that's given by S by S square plus omega naught square. So that's that we have that, and then for real S, we should real S greater than 0. It's a region of convergence, and then the input, the Laplace transform, that's called the x of t is input. Then the x of s is going to be given. So if s is given by 1 over s plus 1. And real s is greater than 1. So that's the region of convergence. And so the y of s is given by the product of the input and the transfer function. And that's going to be given by 1 over s plus 1 times s over s squared plus omega naught squared. And the convergence is now going to be the intersection of these two regions, which is real of s greater than 1. And so what we need to do is now to essentially find y of t, we need to find the inverse transform of y of s. And so the way to do that is to first write this down in this form, the kind of expand out s squared plus omega naught square as s plus 1 s plus j omega naught to s minus j omega naught. So that's your function s. And so we need the partial fraction method, which I hope you've seen elsewhere. And if you haven't, the section 811, which I think I put in the course notes, has the description of how to do it. We write it as 3 different things, as 1 or s plus 1, something over s plus j omega naught, and then something over s minus j omega naught. So these are the 3 terms that we want to have over here. And when we expand it again, if my math is right, it's 1 minus 1 over 1 plus omega naught square, s plus 1, plus 1 over 2, 1 minus j omega naught. And that's the term over here. Plus, and then this is symmetric 1 over 2, 1 plus j omega naught. And so we get these 3 terms over here. And so when we get these 3 terms over here, remember that from the perspective of the transform, this is just some constant A, this is some constant B, this is some constant C, and which are independent of S. And so when we take the inverse transform, all we care about is of the form S plus A, where A here over here is equal to 1. This is going to be A equals j omega naught, and this is going to be A equals minus j omega naught. And so the inverse transform of 1 over s plus A is really straightforward. It's e to the minus A. So 1 over s plus A, it goes to e to the minus at. So using this, we can just rewrite this as A, so minus A, sorry. Just a minute. 1 over s plus A. Sorry. It should be e to the minus. Right. So let's see. So we should have. Okay. So minus. Oh, sorry. This is minus 1. Yeah. So this minus over here comes over there. So it's right. Sorry about that. Okay. So this is A e to the minus t plus B e to the minus j omega naught t plus C e to the j omega naught t, where A, B, and C are those expressions over there. And that's basically what y of t is going to be. Okay, any questions about that? All right, so, okay, so that brings us to the end of the section on transforms. Now, Yeah, so we're not going to use the Laplace transform for for control theory. And so what I'm going to do now is to switch to the exercises in the control theory section, chapter 8. Okay, so the first one is about this the bandwidth management system, and just give me 1 second here. I'll bring up my notes. Right. So what we care about here is we basically think about modeling the system. How do we model the system over here? And so here we have the ISP. So P2P is peer-to-peer traffic. And so we have sort of a link over here, and we have some traffic coming over here, which is peer-to-peer traffic. And, this used to be a big problem about 10 years ago, 15 years ago. Today, you would call it Netflix traffic. It's just it takes a lot of the capacity. So, and this value over here is R%. They want to make sure that not more than R% of the link is occupied by this unwanted traffic, well, not unwanted, but certainly a heavy load on the traffic. If it exceeds R, then you send back what are called reset packets. And then you send reset packets, the connection say, oh, I lost a link, and then the load goes away. And so we want to identify the plant, the command, the control input, the disturbance, and the output. So what are this is the congested link that has potentially too much peer-to-peer traffic on it. And so the plant is the congested link. This is the plant. This is what we care about. So what we want to control is the congested link. So that's why we call it the plant. And then we want to know the command. So the command is essentially what it is that we want to achieve. And the command is the percentage of the links that are reset at a particular time. So we can, the desired maximum percentage of P2P traffic on this thing. So this R%. So this is command is going to be R%. So R is going to be the command. Or you can think of it as a reference value or set point. These are all equivalent terms that we want. So we want to make sure that we never exceed the reference value or set point. I guess in this particular case, reference value is probably more appropriate. We want to make sure that this is the line that's not crossed. So that's also the command. And then we want to look at the control input. The control is this reset over here. So the control value is the number of reset connections. How many reset messages are you sending out is the control value, is the control. And then the disturbance. So the problem with control is that we never really completely control the system. And so we think we control it, but we don't. So just to give an example of a room which has a heater, we want to choose a particular set point, but somebody may open the door or the window and then the temperature changes. So this is sort of the natural variation in the arrival of P2P connections, number of P2P connections. So there's some kind of a natural variation. So, people are going to turn off the browser or turn on whatever it is. And so that's going to cause some fluctuation that you can't really control. And then the output, this is the value that we care about, is again the percentage of the actual percentage of P2P connections, which could be less than R, obviously. Okay, so any questions about this?
Isn't the plan the endpoints, because that's what we're trying to control?
No, we're trying to, well, I mean, it depends on what modeling you have. So the mental model I have is something like this. So we have an ISP, and the ISP has some number of users who are at the ends, right? Who are getting data from some, well, as peer-to-peer, they're actually talking to each other. And somewhere in the network in the middle is this congested link, okay? And whenever this link gets too congested, the ISP is going to send these reset messages to all of the people on that link saying, shut up, this link is too busy. So the plant, it's a matter of notion. You could say the plant includes the end users because they are getting the reset messages, but the place that we are controlling is this congested link. So these are both, I would say, acceptable definitions of what the plant is.
Right. Thank you.
Okay. So moving on. For what we understand, what are the effort and flow variables in the system? So effort and flow are not terms you typically use in computer networks or computer systems. They kind of come from physical systems where, for example, effort would be the so effort is sort of the amount of pressure. So like voltage is an effort variable, for example. So it sort of describes the pent-up demand, and then the pent-up demand causes the flow, right? So there's sort of these, if you're pushing on something, that's the effort, how much you're pushing, and then the causation of that is the flow. So if you have a syringe, something that comes to mind very normally these days, how hard you push is the effort, and how much comes out as a result of that effort is the flow, right? So that's the intuition behind effort and flow. So here, the effort is the how much of a issue is there. So the effort, at least the way I see it, and again one can disagree on this, the effort value for me is basically the number of connections that exceed R, or percentage of connections that exceed number of connections, or the percentage of connections that exceed R, the reference value. So the more we have excess, let's say R is, I don't know, let's say total of connections for the sake of argument that can safely be carried is 100, and let's say R is 20. If you have 30, you have excess of 10. If you have 40, you have excess of 20, and so on. The more the excess, the more the effort you're going to make, that you need to make in order to get the system back to normal. And then the flow as a result of this is the number of resets, or the rate of resets, depending on how you frame it. Typically, you can say number of resets per control period, or the rate of resets is so that's the way I would model it as effort and flow. But I mean, I would be happy to hear what other people came up with.
Can the effort be the number of endpoints trying to make the connection, and the flow be the actual number of P2P connections?
Yeah, the thing is that if the number of connections that if the number of connections that the endpoints want to make is less than R, in some sense, we don't have any need to do any effort. We're not causing any effort. I mean, one could argue that the effort above a certain threshold is what we care about. So in the end, these are modeling choices, and our goal at the end is not to worry too much about the exact modeling, but to make sure that the output, this goal over here, the output is going to be valid. So if you can justify that, you can say, if increase in effort leads to increase in flow, and that's the way I want to model it, then that's fine.
Right. Thank you.
So modeling is, at the end of the day, it's an art. We don't have a rule book that says you must model in this way, you must model the other way. You need to model it, and in any model there will be design choices. Okay, I'm going to model it in this particular way, and at some level, the purpose of this course is not to get a grade, but the purpose of this course is to teach you to think a little bit about systems in a more mathematical way. And to acknowledge that we don't always have the right model. And in fact, what typically happens is you come up with a model, doesn't really work, and you go back and say, oh yeah, I should have done this other thing, and you go back and you model that. And so it's a process of successive refinement that leads to the model. So yeah, so there, this is open to interpretation.
I also have another question. So,
yeah.
So in terms of effort and flow, we are always thinking in terms of it being relative to the control point, right? The command, basically.
Yeah, that's usually the easiest way to think of it. Obviously, there are other things that are going on which are, which have effort and flow, but it's not, if it's not going to affect your command, if it's not something that you care about, it's no need to model it.
All right, thank you.
So, I mean, we're always focused on, what is the command, what is the reference value that we want to achieve, right? That's the command. And we want to execute the command. So if it's not directly relevant to the command, then you say, yeah, well, it's there, but I don't really feel like modeling it. It's not something I care about. Okay. Okay, so let's go to the state space representation. So the question is, what is the state? What should it be? So the kind of obvious and natural way to represent this is the current fraction. So x of t could be the current fraction of P2P traffic. This is really what we care about. Current meaning at time t, current fraction of P2P traffic. And so how does this change? Okay, so here we are given some input. You're saying, assuming that the control rule is to reduce the number of P2P connections by U connections over time t, when x of t is greater than r. Okay, so what we would do is something like this. So we're doing the x dot, so the rate of change of x is going to be given by minus u over t plus w if x is greater than r. Otherwise, it's w, right? So again, here it's a modeling choice. So I said, okay, if the number of conditions exceeds r, well, what I'm going to do is I'm going to reduce the number of connections by u connections over time t. So the rate of change of x is given by u over t. That's basically u over t is the derivative of the number of connections. So that's x dot. And then we're going to have this disturbance term over here because we can't really control that. So W gives us the disturbance that we otherwise have. If it's less than R, sorry, I should use this small r. If it's less than R, then it's whatever the natural fluctuation there is. We're not doing any control at all. That's what it's saying over here. So that's the state space representation. Again, assuming the states, if you use this as the state, then this is what it would be. This is
Are we not mixing fraction of traffic with number of connections here? Because x is the fraction of traffic.
Oh, I'm sorry. Yes,
u is the number of
right.
connections.
Yeah, I'm sorry. I should be careful here. Yeah, I am mixing the two. So. Right, so this should be the actual, sorry, this is the number of connections with P2P traffic. Thank you. with P2P traffic, and then we should say that in the total capacity should be, we need some capacity over here. So it's all a proportion really. So it'll work out, but let's say total capacity is, I don't know, C. Then the fraction is going to be X over C is going to be the fraction. So if, so then we just basically have to say over here, if X over C is greater than R, okay. So yeah, sorry.
By total capacity, do we mean the total number of allowed connections? Like we're assuming we're not
the link, yeah. So we do the link capacity.
But isn't that in like bytes per second? But like we're considering connections per second.
Yeah, so I'm going to define the capacity C is in connections per second. Okay. Connections, number of connections that can be sustained rather than per second is number of connections.
Right. Thank you.
Yeah, you have to keep the units consistent. So that's the total, I can support, let's say 100 connections. Okay. And then the transfer function. So the transfer function here, we're going to basically look at the output. So the output over here is actually the actual percentage or actual number. So let's just say, just keeping consistent with this, let's say y of t is basically x of t. It's this number of connections that's actually there. Then the so we know that y dot is going to be x dot. That's going to be minus u over t plus w if x over c is greater than r and w otherwise. So when we do the transfer function, what we're going to do is let's just for the moment assume that this is going to be true. So we'll just look at that. So then it'll be s y of s equals minus u of s over t plus w of s. And that is going to be the value for when this condition holds over here, if x is greater than r. And so and when we compute the transfer function, we ignore w in computing the transfer function because that's the disturbance that we really can't. We essentially would end up modeling something like the disturbance is inside the input, so we can and it's just a kind of a modified input, so it doesn't really matter. And so the rule of thumb, or if you want to justify it, you can say we just look at the modified input. We're going to say that y of s is going to be, so y of s over u of s, which is going to be the transfer function, is going to be minus 1 over st. So that is basically the transfer function that we have for the system. And again, this is under the condition that x of c is greater than r. But if it's not that, then we just have a disturbance. We know y of t is just y dot is just w, and I mean we're not going to get we will get the same thing, s y of s equals w of s. But there's not too much you can do with this. So typically what we will do is again, pragmatically, what we do is we say, well, if we exceed this ratio, then the system is quote unquote active and we're going to use this transfer function. And if this ratio is not exceeded, we don't do anything. And in some sense, we don't really care what the control is. We're not going to do any analysis for this because it's idle. It's not doing anything. So this is the part that we really care about. And that's the transfer function that we have to care about. Any questions about that?
There's a similar example in the lecture notes.
Yes.
Example 8.4.
Right.
In that, in the step where we take the Laplace transform of both sides, we're doing s minus y0 is equal to and then the right-hand side.
That's right. Yeah, I'm sorry. So what I'm giving here is that I'm assuming that here that y0 is 0. So in the, to be more precise, because this is the Laplace transform of y dot is sys minus y0. So if you take y dot, its Laplace transform is sys minus y0. So technically speaking, we also need to make the assumption that the at the initial point in time, we have 0 connections.
Where does the y0 come in the derivation of of the Laplace transform of y dot?
Why does it come in?
As in, I understand the part about sys, but how does the minus y0 come in?
That's sort of I mean, you can derive it from first principles, which I can't do it. I can, but the rule for differentiation is that
I think the confusion is that it's left out of the derivative rule in the notes in the table.
Oh,
but
right.
The derivative rule really has a minus y0.
Yes, indeed. And I should have, yeah, you're right. Okay, I have to fix that in the table. That's true. So that's the, I mean, there should be an sys minus y0, and I'm just looking at the table and noticing it's not there. It really should be there. Yeah.
The notes in a couple of places talk about, by convention, the equilibrium point being 0.
Yes.
Is that done at all in this question? It seems like the equilibrium point is r.
Yes, in this case, I have set it to r, but yes, we I think I brought that in later. I can't remember when I brought it into this. Yeah, oh, you're right. So again, it's just a transpose, but yes, you're right. We typically, when you talk about stability, we typically want to keep the system at 0. And so we would shift everything, displace it by r. So I think, I don't know who asked that question, but basically we want x equals 0 is typically what we want the system to be at. So we would have to displace it by r, or x by c. Yeah, so yeah, it's true. That's the standard model.
Sorry, another question. So in this question, y is referring to the number of connections, not the proportion, right?
Yeah, so I think I said that over here. So I redid this over here, number of connections. So to be consistent, I want to keep the number of connections. I should make this also to be actual number over here as opposed to percent. There you go. I should just do everything in actual values.
Right, but
R percent. Yeah, the command would be R%, and we just basically we'd convert, multiply that with the capacity to give us the number essentially.
Right.
Or we can use R over C. So these are all constant factors. So it's not a big deal to put them in.
Okay.
Yeah. The goal here is to get the right sort of intuition about what's really moving, and then these constant factors basically go away. Of course, you have to be careful and doing it in practice, but from the perspective of building the system, these are the very small details. Getting the right modeling of what's the command, what's the output is what is important. Okay, any other questions? Okay, so I owe you guys two answers. One is for the table, the frequency shifting, and then I think the question about is the u t minus t naught, or what happens over here with this part where I need to think this through over here. So I will get back to you on this one over here, and then number 2 is the frequency shifting. And yeah, I'll get back to you on that later today.
Sorry, can I have a look at exercise 18 again?
Yeah, sure. 18. Okay.
Yeah, I was wondering. So there is a transfer function just the cosine or the cosine multiplied by the unit function?
I'm assuming that it's a unit function. So this is real system. So it is going to be ut cos omega naught t. Otherwise, it's not going to work properly. Yeah.
All right, so we can just assume for most cases that we can just add the unit function in front of the
That's
transfer
right.
function.
That's right. Yeah. So again, remember for when we're trying to solve the system sort of comes into being at time 0. So it doesn't exist before time 0. And so pre-multiplying by ut is obviously okay because we don't have negative time. We don't have this notion. So we are going from sort of mathematical functions to real systems. And in the mathematical function, you have to look at minus infinity to infinity, but in any real system, it's always going to be ut.
All right.
Yeah,
Cool,
yeah, sure. That's a difference between sort of modeling and and mathematics. So we are kind of making sure so this assumption of y0 is 0 is pretty much a given, well, unless it's specified to be otherwise, we typically assume that the system is nothing is happening at the time that it's created. There's no inputs, there's no outputs. It's just at rest state when it starts. Anything else? Okay, so I wanted to go a little bit more sort of feedback into what's happening in the next 2.5 weeks until the end of term. So this week on Thursday, again, we have the third assessment, which will be on material until what we covered today, which is essentially into system design, not system design, into system modeling. And then we will go next week into, I would expect you to be looking into what are called first order and second order systems and stability. And then there's quite a bit more material and control theory, which we won't have time to go into. And then there's one section called model predictive control, MPC. And I wrote the notes for it, and actually the videos for it I found a very nice tutorial on YouTube from MATLAB, which I linked in, but I suggest you read it, but it will not be assessed. This is just extra material. So the NPC material is just sort of extra material. And the reason it's extra material is in part because I wanted to put it in because this is how we do control systems today. Hardly anybody uses PID control. You need to understand that intuitively, and you need to understand Laplace transforms. But pretty much everything that's done in the field today is model predictive control. But MPC depends heavily on understanding optimization. And I'm not sure all of you have a background in optimization. So I've made that as extra material. So if you don't have time, don't read it now. Take your time to read it later. I think this is something that you will definitely find useful as you go into into using, building real control systems. But it's just that it's not something that I can assess anyway. And then then we'll switch gears and spend the last 2 lectures on simulation. And there I've taken the notes from Professor Richard Gibbons, who used to teach this course. And unfortunately, Professor Gibbons passed away a couple of years ago, but I've used his notes for the simulation part and discrete event simulation. And the part in simulation actually is relatively straightforward. There's a little bit of math there on statistics. And so for those of you who done a statistics course recently, this should be really, really simple, absolutely straightforward statistics. For those who haven't seen it, you may need to spend a little bit more time on it. But if you have done any course in statistics, it should be really straightforward. And that brings us to the end of the course. And so we will have the last assessment on the 18th. And yeah, that's it. So anyway, any questions about that? Okay, great. So in that case, we can end here, and I will get back to you with those 2 things that I outlined. And I'll talk to you next Tuesday. Okay. Thank you.
Thank you.
Thank you.
Bye-bye.
Thank you.